Yeah, the last topic of this chapter is surface acidity of solid, pH of zero charge, and also I will give you another information about the theory behind this colloidal stability. Okay, um, related properties to geology, environment science, and ceramics, mineral, clay, organic surfaces behave as acid or bases. When you think of acid or bases, your knowledge must not be confined only to um, you know the ordinary acid or bases. Even um, mineral or clay or even the solid surface, solid can be behave as acid or base. Okay, you know understanding is not difficult. Okay, let's say just the simplest case is the silica surface. Silica, the main uh, you know component is what? SiO2. Okay, that's the silica. Silica is the main what component, main ingredient of sand or glass. Okay, the glass made out of pure silica, pure SiO2 is called fused silica, or if the structure is has a crystal, that is called quartz. Okay, and here this the surface of a silica, you see, the surface has this structure, Si and OH2 plus. Okay, Um, when this silica is uh, what put in a strongly acidic solution. Okay, proton now goes to this silica surface, and the surface takes this one positive charge. Okay, since it has proton, and this silica, the proton is dissociated into solution, yeah, from the surface, and leaving this neutral silica surface. Okay, so this one is acidic. This one behaves as acid. And also we can define the equilibrium constant like that. All right. And when this silica surface is in a strongly basic solution, and then this proton is deprotonated. Mm, Okay, okay, this one, Mm, and it becomes negatively charged, and proton is released. Okay, for this one we can uh, write the equilibrium constant Ka2. All right, so uh, don't take it as strange, even solid can be behave as acid or base. Okay? So we apply the concept of isoelectric point. Okay, isoelectric point, mm, the concentration of this one and this one is positively charged species, and negatively charged species concentration is the same. Okay, and then solution pH is given by just a simple equation. Okay, pH is 1/2 of pK1 plus pK2. Okay, so it leads us to naturally to the colloids. Okay, the colloid. mm, Colloid is a nano particle, okay, whose particle size is 1 nanometer, between 1 nanometer and about 500 nanometers. Okay, someone says maybe it extends to 1 micrometers. Okay, yeah, that particles are called colloid. Okay, so in today's term, they are nanoparticles. Many people are interested in the nanoparticles. Okay, yeah. And actually, colloidal particles have been quite well known, long time. Even quite a long time ago, people studied the stability of colloids. Okay, there are we every day we see or we use colloids. Okay? For example, your cosmetics. Okay, they are all colloids. and ink, they also colloid. And you see our tofu, okay, your favorite food is also colloid. Yeah, colloid is everywhere. Aerosol is colloid, okay. So so colloids, when colloid is different from a solution, okay, because there are particles, okay. The particles are not uh, completely dissolved in solution. They are simply dispersed in a dispersed medium, okay. So, but colloid particles are quite stable. You see, the milk is also colloid. Yeah, the people wondered why the colloidal particles are quite stable. Mm. You know, colloidal particles are size, as I said, is between 1 nanometer, up to 500 nanometers. Yeah, they are subject to a gravitational force, and then colloidal particles now, you know, um, get together, and they must be, they what sink down to the the bottom, right? But actually, that doesn't happen. You see, they these days people don't use ink very much, but the ink, yeah, is colloid, right? But how long? No matter how long you wait, hmm, you don't see, the ink, the colloid is separated from naturally, yeah, from the ink, right? Never. Uh, you drink milk every day, right? But milk never, you know, they never undergo phase separation. Okay, they are stable indefinitely. Okay, and people wondered why those colloidal solutions or colloidal or media are stable. Why? Why is that so? Okay, so there is a very famous theory behind the colloidal stability. This is a special lecture, but I think this is quite important. Okay, colloidal particles are stable. Okay, for a very long time. Okay, for indefinite time. Yeah? To understand, colloidal, particle stability, you have to understand two forces working on the colloidal particles. Okay, let's see. Uh, they are colloidal particles, or even they are a species, differently charged. Okay, what forces are working for colloidal, or in general, between two surfaces. Okay, one is double layer interaction. Okay, the other one is van der Waals interaction. Okay, double layer interaction is what? They are electrostatic repulsion. Okay, let's see, electrostatic attraction and repulsion occurs depending on which charges they take. Between oppositely charged species, electrostatic attractive forces are working. Okay, if the particles have the same charge, there is all the time electrostatic repulsion. Okay, the Coulombic principle. Coulombic force dictates that the force between two species is what, inversely proportional to the uh, what, the distance squared. Okay, but when they are mm, oppositely charged, there is attraction. If they are similarly charged, negative negative or positive positive, there is a repulsive force. Okay, yeah, this is a general concept. Okay, this is this principle mm, applies to these spherical particles, or to these two flat surfaces. Okay, yeah. Here, this is called double layer interaction. Okay, double layer interaction, yeah, is given by this equation. All right. The important that is that interaction is exponentially decreases. Okay, here it is. This is a proportional constant, and it is exponentially decreases with respect to the separation h. Okay, yeah. And there is another force. But since the the colloidal particles are all the similarly charged, okay, let's say you you prepare this silica surface, okay, and then you put those silica particles in water solution, in water, and then what? Now all the silicas are the same, so they are all the similarly charged, okay, positively charged and or maybe negatively charged, okay, they are all similarly charged. As long as we are dealing with one kind of colloidal particles, okay, they are all repulsive force, okay, here. And there is another force, that's attractive force. That force is van der Waals interaction. Yeah? In the general chemistry course, yeah, you heard the van der Waals interaction, okay, in when you are dealing with a gas, okay, there is van der Waals. He's a very famous physicist. He received the Nobel Prize, okay, for his work, okay, on force. Yeah, van der Waals forces are all the time attractive force, okay, and this van der Waals force is a very short range force. That means that two particles, okay, when they what get close each other, and then van der Waals force, this force working, and they are all the time attractive force. Okay, think about the helium. Hmm? Helium is very small. Hmm? Helium is very inert. Okay, but helium is also liquefied at very low temperature. Okay, at 4 uh, the Kelvin, helium becomes a liquid. Yeah, becomes a liquid. Becoming a liquid means what? Hmm? Helium. Hmm? Between helium atoms, there is a attractive force. Okay, yeah. Why? Why there is attractive force? Because yeah, that force is called van der Waals force. Okay, that because of polarization. Okay, the important is that van der Waals interaction is all the time attractive force. So two different kinds of forces are working in between colloidal particles or any surface. Okay, here, and van der Waals force is expressed by this equation. Okay, yeah. So total force interaction energy is here is the energy. Okay, W is energy work. Yeah, this double layer interaction plus van der Waals interaction. Okay, here this figure illustrates okay how two different forces are working. Here double layer interaction force is exponentially decrease. Okay, you see the y-axis is force and the x-axis is separation. Yeah, it's a h value here, right? And here the positive value means the repulsive force and negative value is attractive force. Okay, and the van der Waals force working like that. Yeah? When two surfaces are separated, van der Waals force is very small, and then when they are brought closer, and then they suddenly at the very close, van der Waals attract force increases very rapidly. So total force is represented as this green line. This is a total force. Okay, what is the uh, and you know to make the colloidal particle unstable, those particles must put together, okay, and they sink uh, in the bottom, okay, to for those particles get together and make a larger or larger the particle, and then due to the gravitational force they may sink to the bottom. Those particles should overcome, yeah, this energy or this force, okay, this force. Otherwise, ordinarily, particles are separated, they are brought together, not actually contact. Yeah? because they don't have enough force or enough energy to overcome this here. All right, you understand? Okay. To make the colloidal particles unstable, there are several ways. The one way is to increase temperature. Okay, increasing temperature is what provide energy, external energy to the colloidal particles. Okay, and then the colloidal particles now overcome this attractive what this force, right? So they can be put together, yeah, and they sink to the bottom. Or another way, another easy way is to add the salt concentration. Okay, when salt is added to the system, and uh, the double layer interactive attraction becomes weaker and weaker. Okay, this one weaker and weaker. So this one double layer, this interaction becomes it's a weaker and weaker, and then finally it becomes very small. Yeah, but the Van der Waals interaction, actually it doesn't matter, okay, whether you add salt or not, right? Van der Waals interaction is quite constant. Okay, so total this force becomes smaller and smaller. Okay, here this original force, and when you add yeah, with increasing salt concentration, it becomes smaller and smaller. Okay, and there's a very low, very small this one activation energy, so it is easy to overcome this one. Okay, and then these particles are put together, okay, and becomes unstable. All right, yeah. This explains why our grandmother or your mother, when they make tofu, um, the tofu. Tofu is made of beans, yeah. The beans is very finely ground, and then to make a tofu, usually, your the salty water, okay. You pour the salty water to the colloidal, mm, the bean colloid, and then suddenly, there is some kind of the particles are put together and grows. Okay, yeah. That is explained quite well by this model, right? This model is called DLVO. They represent initials of four people who developed the theory. Okay, Deriagin, Landau, Borway, and Overbeek. Okay, yeah. the, the core of the theory is the two forces are interacting together. Yeah, Van der Waals attractive force and double layer repulsive force. Okay, to decrease the Van der Waals attractive force is not affected by increasing salt concentration, but this one double layer interact this repulsive force becomes weaker when you add this salt. Okay, yeah. Okay, this is end of chapter 9, and here is the homework problems. Okay, you solve these selected problems and upload on the eCampus. Okay.